Hello students, in this video let us cover diffraction of light. Diffraction of light. To understand diffraction of light, let us revise few concepts. First one is wavefront. Wavefront is locus of points which are in phase, isn't it? If this is the point of disturbance, surface of water, point of disturbance, then ripples are generated. So these ripples are nothing but wavefronts. So due to point source, if this is point source of light, then according to ray optics, this point source gives diverging rays like this. Isn't it? Now, using wave optics concept, the same diverging rays should be represented by wavefronts. So these are spherical wavefronts, part of spheres. Okay. So these are spherical wavefronts. So due to point source of light, spherical wavefronts are generated. Spherical wavefronts. And these spherical wavefronts are analogous to diverging rays. Spherical wavefronts, they are nothing but diverging rays. Diverging rays in ray optics, spherical wavefronts in wave optics. So both of these represent light from a point source. Okay. If there is a distant source, distance is more means from this source light rays are parallel in nature, isn't it? So this is how we used to draw parallel rays or beam of light. So simply we say, if source is at infinity, means distance of the source from this point of observation is more, then that results in parallel beam, parallel rays, beam of light. In this case, parallel rays. Okay. So in laboratory condition, parallel rays are obtained from a point source. If this is a source, and this is a lens, what is the condition? This source should be at the focus of the lens. If source is at the focus, F, then these diverging rays from this source becomes parallel. This we have understood in ray optics. So these are diverging rays, and after refraction through the lens, they become parallel to each other like this. So source is at infinity, parallel rays. In laboratory condition, source should be at the focal plane of the lens, nothing but at the focus of the lens, then diverging rays will become parallel. So this is according to ray optics. The same parallel beam of light or parallel rays are represented by wavefronts. So these are the wavefronts. If we draw lines parallel to each other and straight, then they represent plane wavefronts. Plane wave fronts. So in the same diagram, if I try to draw plane wavefront, then this is one plane wavefront. This is another plane wavefront. In the beginning of wave optics also we have understood this. So these are plane wavefronts. Instead of writing in 3D, draw straight and parallel lines. They represent plane wavefronts. Okay. Second revision topic, equations. Constructive interference. Constructive interference. So interference is said to be constructive if intensity is maximum. Intensity is maximum. Okay. And condition for constructive interference in terms of phase difference, 2n pi, where n is 0, 1, 2, 3, etc. So phase difference should be in terms of pi. Similarly, path difference delta equal to n lambda. Substitute 0 here, we get 0, 1, n equal to 1 in this, we get lambda, then 2 lambda, 3 lambda, etc. So if path difference between the waves is an integral multiple of the wavelength, then that results in constructive interference where intensity is maximum. In short form, crest of one should fall on crest of the other, or trough should fall on trough of the other. Now understand this. This is first wave. This is first wave. This is second wave. This is amplitude A. This amplitude B. See, crest overlaps on crest, trough overlaps on trough, crest on crest, trough on trough. So if these two waves interfere, they interfere constructively because of this condition, or because of this condition, or because of 2n pi. Okay, so this results in constructive interference. Now for destructive interference, intensity should be minimum. And phase difference between the waves, interfering waves, should be equal to 2n plus 1 into pi. Again, where n is 0, 1, 2, 3, etc. And path difference between the waves should be 2n plus 1 into lambda by 2. Pi in place of pi, lambda by 2. Substitute 0, we get 2 into 0, 0, lambda by 2. Substitute 1, we get 3 lambda by 2. After that 5 lambda by 2. 7 lambda by 2. So this is for path difference. Now for phase difference, substitute 0 in the first equation, we get pi. Substitute 1, we get 3 pi. Substitute 2, we get 5 pi, 7 pi, etc. So condition for destructive interference in terms of path difference, destructive interference in terms of phase difference. Now how to visualize destructive interference means, this is first wave. Initial phase nothing but this point corresponds to 0. Now second wave. Second wave should be something like this. Initial phase of this is pi. 0, pi, difference of these two is pi. If amplitude of first wave is A, amplitude of second wave is B, then resultant amplitude is A minus B. In the first case, resultant amplitude is A plus B. If it is A plus B, constructive interference. A minus B, destructive interference. Okay. Now, crest on trough, trough on crest, crest on trough means destructive interference. Crest on trough or trough on crest. This results in destructive interference. Try to visualize constructive interference or destructive interference based on equations or wave patterns. Okay. Now let us start with diffraction of light. Go through this statement. Diffraction of light is the bending of light at sharp edges and encroachment of light into the geometrical shadow. Students, again go through this statement. After that, see, there is a sharp edge. So this is a knife edge. This is the sharp region. Knife edge is placed like this. Okay. Incident is parallel rays. This is the simplest case. If source is at infinity, what we get is parallel beam, nothing but parallel rays. If parallel beam of light falls on the knife edge, then if it is a metal knife, most of the light rays are cut off, and those light rays which are not falling on the knife can fall on the screen. This is a white part, white region, some surface to get the or to collect the light. So this is the screen. Okay. So this light can fall on the screen. If light can fall on the screen means on the screen there will be illumination, and this region is the shadow region, isn't it? So this shadow is called geometrical shadow. Why it is called geometrical shadow? Because geometrical optics is used. Geometrical optics is nothing but ray optics. So in ray optics, we use angles and lengths, nothing but geometry. That is why this region is called geometrical shadow. Now students, concentrate. When light falls on the knife edge, there is illumination on the screen, and this is the shadow region. This shadow region is called geometrical shadow. But when we do this experiment in laboratory, illumination can be observed on the screen in this portion. No issues in that, right? But light also seen in the geometrical shadow region. See, there should not be any light here because there is a knife edge. Then also we get light. So this encroachment of light is due to diffraction. This is due to diffraction. Now, how to show illumination here? this light ray should be bent like this. This is the only way we can show illumination here. See, light ray bends at the sharp edges. So this bending of light is called diffraction of light. Now let us understand why there is encroachment of light. Let us understand another important factor in diffraction. Let me use this small experimental setup. Observe the diagram. There is a slit here, screen. This is incident plane wavefronts. So in laboratory, using a convex lens and a source, we can get parallel beam of light. So plane wavefronts are falling on the slit, and plane wavefronts will become spherical wavefronts. Can you observe? Plane wavefronts, spherical wavefronts. So plane wavefronts to spherical wavefronts is nothing but diffraction, because spherical wavefronts can spread, but plane wavefronts cannot spread. So this is spherical. Also observe, if these are the wavefronts, then these are the crest points. If there is a wave like this, this is side view, these are crest points, isn't it? And these crest points form this wavefronts. So if I draw dotted line in between two smooth lines, then this dotted line represents trough points. So let me use only crest points. So these are the wavefronts, plane wavefronts. Students, what is the distance between adjacent crests in a wave? Distance between adjacent crests is wavelength, isn't it? So this is lambda. So here distance between adjacent wavefronts is lambda. Lambda provided if it is smooth and smooth line. If it is smooth and dotted line, it is lambda by 2. Fine. Now observe wavelength and observe the slit width. So slit width is comparable to wavelength. So lambda is comparable to slit width. So D stands for slit width. D is slit width. Okay. Now in the second experiment, in the another setup, let me increase the width of the slit. When slit width is increased, compare these two diagrams. With respect to this width is more, but I am keeping the wavelength same. So this distance is lambda. This is the slit width. With the increase in slit width, this spread is less. Here spread is more. Suppose slit width is 5 cm. We should expect illumination on the screen whose width is 5 cm, isn't it? So we should expect this, a bright patch on the screen whose width is equal to width of the slit. But we can expect, or we can see light spread on the screen. If this is 5 cm, here to here it's about 10 cm, then this spread is about 25 cm. So 5 cm slit width gives 25 cm illumination. I am giving all these numbers to understand. Okay. So 5 cm width can give 25 cm, means 5 folds. Now come to this. Slit width is more. Lambda is very much less than small d. Lambda is very much less than small d means spread is also less. So if slit width is about 10 centimeter, we should expect illumination of about 10 centimeter. Let this be about 5 centimeter. This is about 5 centimeter. Observe, 10 centimeter slit width gives about 20 centimeter illumination. So 10 centimeter to 20 centimeter illumination. It is just two folds. If slit width is less, then it is 5 folds. So concentrate on these two. If wavelength of light is comparable to the slit width or gaps, then or size of the obstacle, then diffraction is more diffraction. If wavelength is very much smaller than slit width, size of the obstacle, then less diffraction. So this is one important point. So because of this reason, diffraction in sound waves is observed more in day-to-day life than diffraction of light. How to imagine diffraction of sound? If there is a vehicle sound, vehicle horn sound, somebody is talking in the next room, we can hear sound means those sound waves can bend at the edges, nothing but windows, doors. At the window frame or door frame, the sound waves can easily diffract. As a result, we can see diffraction of sound. We can hear sound. But light, wavelength of light is very small compared to the slit widths formed between windows and the frame, doors and the frame. That is why light diffraction is less observed. Two observations. Lambda comparable to slit width, more diffraction. Lambda very much less than slit width, less diffraction. Second observation, diffraction is observed more in sound than light. Does the wavelength of light affects diffraction? Answer is yes. So before going into the equation, let us understand how wavelength affects diffraction. Students, observe, there are two experimental setup. This is the slit width, slit. This is one more slit. Widths are equal. These black lines are wavefronts, parallel beam. Plane wavefronts represents parallel rays, parallel beam of light. So in the first case, red light is used. In the second case, blue light is used. Red means longer wavelength. So lambda for red is greater than lambda for blue, isn't it? So wavelength is more means this is how diffraction can be seen on the screen. So this is a pattern on the screen. If slit width is about 5 centimeter, then we get much broader bright patch. So this bright patch followed by few more patches on either side of the central gives the diffraction pattern. So this is diffraction pattern due to blue light. This is called principal maximum. In the next topic, let us use the nomenclature properly. For time being, this is called the principal maximum. This is first minimum, first maximum, second minimum. Minimum means 0 intensity. This is second maximum. Similarly, principal maximum, first minimum, first maximum, second minimum, second maximum. So every time we cannot keep shading the diffraction pattern. Instead of that, we prefer graphs. So let me plot a graph. Let me represent this pattern using a graph. So let me draw graph of intensity along y-axis versus distance. Okay. So this is y-axis, intensity, x-axis, distance or path difference. For time being, let it be distance. Okay. Intensity is maximum at the center. Intensity is maximum at the center. So intensity is maximum at the center. On either side, intensity decreases till here. Again, intensity increases. But intensity at the center of first maximum is less than the intensity at the center. Then minimum. There is small band. Then minimum. Now let me draw the pattern. See, intensity decreases and becomes zero intensity. On the other side also, intensity decreases, then intensity is more, again decreases. If you draw carefully, then height of this should be same as height of this. Okay. For time being, this is sufficient. So when we use graph like this, then this represents a graph of intensity versus path difference in the case of diffraction of light. This is called principal maximum, first minimum, first secondary maximum, nothing but first maximum, second minimum, second maximum. Similarly, principal maximum, first minimum, first secondary maximum, second minimum, second secondary maximum. Okay. So it's a graph of intensity versus path difference. Let me write path difference. I'll explain this later. So if wavelength is more, diffraction is more, nothing but width of the principal maximum is more. If wavelength is less, shorter wavelength, diffraction is less. Width of this principal maximum is less. Single slit diffraction. Let this be a slit. This diagram is important compared to all other diagrams in diffraction. This is single slit. Now parallel beam. These are the rays from distant object. Rays from distant object or source means parallel beam. Parallel rays. Beam is bunch of rays. Okay. These are the rays. Therefore, draw arrow. So these rays fall on the cardboard with narrow slit. So these rays are cut off, whereas only few rays can pass through the slit. Let screen be far away from the slit. So screen is at infinity. Screen is at infinity means it is not infinite distance as it is said in mathematics. In mathematics, infinity means not defined, whereas in physics, infinity means distance should be more. So let me not write the screen. Okay. So if there is a point on the screen, so to see illumination at point P, we should draw these rays. These are diffracted rays. Since distance of the screen is more, students, please understand, since distance of the screen from the slit is more, these diffracted rays must be parallel to each other. See, incident is parallel, diffracted rays are also parallel, means this is a special type of diffraction called Fraunhofer diffraction. Fraunhofer diffraction. There is another kind called Fresnel diffraction. It is not there in your syllabus. So Fraunhofer diffraction is due to incident parallel beam and diffracted parallel beam. Now consider the central. Consider the central ray. This is the direction of incidence. This angle is the angle of diffraction, theta. Width of the slit is d, small letter d. Then path difference between these two extreme rays, first and second. Path difference between the extreme rays reaching point P. P is some point on the screen. So path difference between these two rays is given by d sine theta, sine of the angle of diffraction. D is width of the slit. So d sine theta gives path difference, where d is width of the slit and theta is angular position of P. At what angle with respect to median? See, light is traveling straight. At what angle P is found? So that angle is measured for the median ray, nothing but the central ray. So this angle is angular position. So with respect to the central ray, angular position is taken. So this angle is theta. Okay. Remember, distance of screen from the slit is more. But to understand, I am keeping the screen close to the slit. Okay. If this is the screen, then because of this slit and incident light, pattern is seen on the screen. Something like this. Since we can't understand from the pattern, it is appropriate to draw the graph. So let me draw the graph. Intensity. This is for the path difference. Intensity is maximum at the center. On either side, intensity decreases. Maximum. Minimum intensity is at minimum. First minimum. Second minimum. See, height of the intensity curve should decrease. Nothing but intensity decreases as we move away from the center. On the other side also. So this is a graph of intensity versus path difference. Now how to find this path difference? For time being, let me mention the path difference. After that I'll explain how to get path difference. Okay. So this diagram is important. Now whatever I write, you don't have to copy. This central is called principal maximum. Principal maximum. College principal, principal main, principal maximum. And this is called first minimum. This is second minimum. Between first minimum and second minimum, there is a maximum. Let me write that maximum here. This is first secondary maximum. Why I am using this secondary term? Since the first one is mentioned with principal, so the subsequent maxima are nothing but secondary maxima. This is first secondary maximum, second secondary maximum. Principal maximum, first minimum, first secondary maximum, second minimum, second secondary maximum. So you should learn these names. Next, if you carefully observe, width of maxima decreases. So width of maximum decreases with order. With order means when we go away from the center, the width decreases. Okay. Similarly, width of minima, if you observe, width of dark region increases. Width of minimum increases with order. So from the single slit, we expect bright patch whose width equal to width of the slit, but we get broader patch of light, which is called principal maximum. Along with this bright patch, on either side we get few more patches. So these are called first secondary maximum, second secondary maximum, etc. So in between two maxima there should be a minimum. So this is first minimum, second minimum. Okay. Students, copy this, and these names are required to understand to solve problems. Now let me explain formation of this principal maximum. The explanation is little bit lengthy, but from the beginning try to understand. Okay. So let me explain in 3 steps. The formation of principal maximum, then the formation of minimum, first minimum, and the formation of first secondary maximum. Now let me explain formation of principal maximum. This is the slit, and this is for the screen. These are the incident rays. Now consider these two extreme rays which are close to the obstacle. This is the direction of incidence. This line is nothing but median. This point O, this is O. I should show rays reaching O. Okay. This ray undergoes bending and reaches O like this. This ray also undergoes bending and reaches O. I am not writing the central ray. Okay. This is first ray. This is second. So consider waves from these 2 points. Let me represent this point by A and this point by B. Wave from A travels some distance to reach O. Similarly, wave from B also travels the same distance to reach O. If you can see, you can easily construct an isosceles triangle. Isosceles triangle means these two sides are equal. So waves from A and B are traveling equal distance. They travel equal distance. For example, 4 meter from A to O. B to O is also 4 meter. First path AO 4 meter. Second path BO 4 meter. What is the path difference? Path difference is 0. And 0 path difference corresponds to constructive interference. That is why these two extreme rays will interfere constructively at O. So path difference, we should write it as d sine theta. So path difference equal to 0 is the condition for principal maximum. Now let me consider a point just below A. I can get another point above B. So waves from these 2 points also travel equal distance to reach O. If they travel equal distance to reach O, then again path difference between these 2 rays is 0. Students, put effort and try to understand, try to follow all the statements. If you consider any point between A and this center, then you will get another point between center and B, where waves from those 2 points will interfere constructively at O. Means you consider any wave in the upper half, you will get another wave in the lower half where those 2 waves interfere constructively. That is why the intensity is maximum. Intensity is maximum at the center. Of course, this diagram is not required for you. This is to understand. This is sufficient. If you don't understand, please pause and replay. Replay only this part and try to understand. So path difference d sine theta equal to 0. Now d cannot be 0, isn't it? D is not 0 because there is slit. Sine theta must be equal to 0. If sine theta is 0 means theta equal to 0. See? If light is traveling straight, only at that region intensity is maximum. That is why we get this peak, and on either side the intensity should decrease. Okay. So where lies the maximum intensity point on the screen means it is always on the median. Observe, first minimum is not on the median. This is the median. This first minimum is not on the median. So let there be first minimum somewhere here. Okay. So I should show bending to explain first minimum. So this is the refracted ray, refracted ray, refracted ray, incident ray. Now let me divide this gap into two equal halves. I am trying to explain first minimum, students. Please concentrate. Now, what is the path difference between these two means? I should draw perpendicular. This extra length is the path difference. Okay, this extra length is the path difference. Now, let me draw the pattern. This is wave from A. This point is B. The center is C. Let me draw a wave from A, a wave from C, a wave from B. So you should draw carefully to understand. Observe, path difference between A and C means this wave. You can see half a wave. So path difference between A and C is half a wave is lambda by 2. This is for destructive interference. Path difference between C and B, next shaded portion, C and B is lambda by 2. Again, lambda by 2 is for destructive interference. So if you consider a wave from A and a wave from C, these two waves interfere destructively because path difference between the waves is lambda by 2. That results in first minimum, dark region. Okay. Now, consider a wave just below A from this point. You'll get another wave from this point where path difference between these two waves is also lambda by 2. Therefore, when these two rays or waves interfere, then they interfere destructively at this point. So there is destructive interference at this point. So if you consider any wave, students, please follow. If you consider any wave between A and C, you'll get another wave between C and B, where path difference between those two waves is lambda by 2 and they interfere destructively. That is why a dark region is formed. Students, don't get confused between diffraction and interference. They interfere destructively means there is no distinction between interference and diffraction. In the last topic, let us go through the differences between interference and diffraction. They interfere destructively. Every wave between A and C will interfere destructively with any other wave between C and B. As a result, there is a dark region. That dark region is first minimum. Next is first secondary maximum. First secondary maximum is this peak or this ring. This is the slit screen. Observe, first maximum is some more away from the median. First central, first minimum, after that first maximum. Let me divide AB into 3 regions. To understand first secondary maximum, we are using this explanation. Okay. Now, first secondary maximum. So I should show more bending. More bending. let me draw dotted lines, reference lines. They give the path difference. Okay. This is wave from A. This is wave from B. This is wave from one more point D. This is wave from B. This is C. This is D. Okay, fine. Observe, path difference between A and C is this shaded region. Crest is falling on trough. So path difference between A and C is lambda by 2. Path difference between C and D is also lambda by 2. C and D is lambda by 2. Between D and B, this shaded region, between D and A is lambda by 2. Now, consider wave from A and wave from C. They interfere destructively because path difference between them is 0. So this get cancels with this. So if you consider any wave between A and B, you'll get another wave between C and D, where path difference between those two waves interfere destructively. Okay. Now, there are waves between D and B. They will interfere and give some intensity at first secondary maximum. That is why intensity at first secondary maximum is not same as that at the principal maximum. So we are using these diagrams to understand first secondary maximum, first minimum, principal maximum. Okay. Now, what is the path difference between these two extreme? Path difference between A and C is lambda by 2. Between these two, lambda by 2. Between these two, lambda by 2. Total is 3 times lambda by 2. So path difference for first secondary maximum is d sine theta equal to 3 lambda by 2. In general, path difference for nth secondary maximum d sine theta equal to 2n plus 1 into lambda by 2. 3. 2n plus 1 lambda by 2. Now let me write. For principal maximum, d sine theta should be equal to 0. Path difference should be equal to 0. For first minimum, d sine theta, path difference should be equal to lambda. For second minimum, d sine theta equal to 2 lambda. And for first secondary maximum, d sine theta equal to, this is 0, this is lambda, this is 1.5 lambda. 1.5 lambda is 3 by 2 lambda. For second secondary maximum, d sine theta equal to 5 lambda by 2. 5 by 2 lambda. Let me consolidate all this. This is the diffraction pattern. Principal maximum. Condition for principal maximum. Path difference. D sine theta should be equal to 0. So in interference, we used to represent path difference by just symbol delta. Now let us use d sine theta. Condition for nth minimum, path difference d sine theta equal to n lambda. where n is 0, 1, 2, 3, etc. Substitute 0 here, we get 0. Substitute 1, lambda, 2, 2 lambda, 3 lambda, etc. But part difference 0 is for principal maximum. But here 0 is there. That is why 0 should not be included, means n should not be from 0. So in the case of diffraction, n is from 1 to 3. Recall in interference, we used to write 0, 1, 2, 3. Now it is from 1 to 3. Okay. Now condition for nth secondary maximum. D sin theta should be equal to odd number 2n plus 1 into lambda by 2. Again n equal to 0, 1, 2, 3, etc. Substitute 0 here, we get lambda by 2. n1 3 times lambda by 2, 5 times lambda by 2, 7 times lambda by 2. Lambda by 2 is not there, means n should not start from 0. So this is the condition for nth secondary minimum, nth secondary maximum. This is the condition for nth secondary maximum. D sin theta 0, d sin theta n lambda, d sin theta 2n plus 1 lambda by 2. Students, after the statement of diffraction, what you need is these three statements. Okay. So please go through the video carefully, concentrate and understand. This is one of the tricky topics in 12th standard physics. Okay. But it is not difficult, but it is tricky. If you know basics that I taught you in the beginning of the video, then it is very easy to understand these concepts. Try to visualize.